Hello everyone, welcome to the week 8 for the deep learning problem solving session. So in today's session we will continue to solve some more problems on convolutional neural networks. So let us start with our first problem. So these will be kind of similar with the one we solved last day as the last exercise. We will take a few more that type of problem to get the completely clear idea about the convolutional neural network. Mostly we will focus on that for today. So if you have any doubts at any point, you can just stop me. So the first problem is the input image has been converted into a matrix of size 64 cross 64. And a kernel or filter of size 5 cross 5 with a stride of 1 is used with no padding. Then what will be the convoluted matrix size? So here our input is 64 cross 64. So last day we wrote a formula for this to get the size of the convoluted matrix from the size of the input matrix. So if our input matrix is of size n cross n and we are doing, let's say, padding of p on each side, so total padding is 2p, and our filter is f cross f and stride is, let's say, s, then the size of the convoluted matrix, let's say, that will be n dash cross n dash. So that n dash will be equals to n plus 2p minus f by s, floor of that, plus 1. That's what we derived or we came to know last day. This formula will be the case for computing the size of the convoluted matrix. So here in this particular problem our n is 64 and you have been mentioned that there is no padding. So p is of course 0 and your filter size is 5 cross 5. So your f is 5 and your stride is 1. So this will be 60. So the dimension of your convoluted matrix will be 60 cross 60. So your matrix size reduced as there was no padding involved. So it became 60 cross 60 from 64 to 64. Okay. Now let us move on to the next one. Next one is also similar. So here the filter size of 3 cross 3 is convolved with a matrix of size 4 cross 4 with stride 1. Then what will be the size of output matrix if valid padding is applied? So let us first see what is valid padding is. So when you go for implementing these convolutional neural networks, you will find one argument for padding that you can specify for these convolutional layers, and generally that will take two types of options, either valid or same. So same means the padding will be such that after passing through the convolutional layer, the size of the matrix will remain same. So if initially it was a 4 cross 4 matrix like mentioned here, if you are specifying that the padding is of type same, then after passing through the convolutional layer, your matrix will remain of the size 4 cross 4. But so to keep that in the same size, whatever necessary padding has to be done, that will be done if you specify padding as same. But if you specify it as valid, then basically there will be no padding done. So your convoluted matrix will be smaller in size along each of the dimensions as compared to the initial matrix. So this is just same as your size is reducing, so there is no padding involved, then you specify it as valid padding. So in this case also, like the previous one, we can compute the size of the output matrix. So here your input matrix size is 4, so n is 4. since we are doing valid padding, there is no padding involved. So, here n is 4, your p is 0, your filter is 3 and your stride is 1. So, your n dash will be 4 minus 3 by 1 floor plus 1, so 2. So, your output matrix size will be 2 cross 2. You can also visualize this if you just to get the idea. So, let us do that once. So, let us say this is your input matrix, which is a 4 cross 4 matrix. This is a 4 cross 4 matrix. Now, let us say your filter size is 3 cross 3. So, at the first position your filter will sit here. So, this entire 3 cross 3 will be covered by the filter. All these 9 cells will be covered by the filter, combined by the filter coefficients to give you the first output. So, these 9 cells will give rise to the first cell in the output matrix. Now, your stride is 1. So, next your filter will shift by 1 position. So, next your filter will sit at here. Now, these 9 points will be combined by the filter coefficient, and in the output matrix you will get the second value. Now, once this is done, in the next step, so horizontally you have moved your window, you moved your filter as far as it can go. So, now you will have to move it first vertically downwards, then again do the horizontal screening. So, first initially for the first layer this was here, initially it was at the first 9 cells. So, now if you move it downwards by the stride amount, which is 1. So, next your filter will be placed here. So, this again will give you the value here, and lastly, let us say I will take black. So, lastly again you have to shift it horizontally and your filter will be placed here and you will get the output value here. So, this will be the final 4 cross 4 matrix that 2 cross 2 matrix that you will get at the output from the initial 4 cross 4 matrix due to the convolution with the filter of size 3 cross 3 with the stride of 1.
Madam, stride means we have to do it horizontally as well as vertically.
Yeah, so if it is a 2D input, so we will do first horizontally, we will cover the entire stretch, then move it one step vertically, again cover the entire horizontal stretch and go on like that. So, if you had one more row here in the matrix, then you would have again moved in the next step you would have moved the filter here and get the value over here, like that you have to do. But if it is a 1D array, you are doing 1D convolution, then there is no vertical movement involved, only you will have to move along the horizontal direction.
When actually we have to go for padding, madam?
So, padding is if you don't want, so if you do not do padding, then initially you had 4 cross 4, that went down to 2 cross 2. If your use case requires you maintain the size, you want the output of the convolution also to be of 4 cross 4 size, in that case you will have to do padding. Whenever you are required to maintain the size, you do not want to reduce it.
Madam, if image is 4 cross 4, output without padding it will be reduced, no madam?
Yeah, without padding.
So, how much we have to pad it, how do we come to know?
So, if you can compute it from that same formula that we are using. So, the formula I gave, this. So, this n dash is your output dimension. So, this side is n dash, this is n dash, each side is n dash, and initially it was n cross n. So, if you want to keep n and n dash same, let us say initially your n was 4. So, I will do it here. So, you want to keep your output size also 4 cross 4. So, your n dash also you want to keep it 4, and your n was already 4. This p is the padding, and your filter is 3, and let us say stride is 1. So, you can simply solve this to get the value of p. So, that amount of p is the padding that you have to do on each side. So, this side you will have to pad p, this side p cells has to be padded, this side also p has to be padded, like that. Here also p, like that you have to pad to keep it at the same size.
Okay.
Any other doubts from anyone, you can also ask.
Filter and the kernel both are same, madam?
Yeah, both are same basically.
Oh, okay.
So, in this case it is coming 1. Okay, then let us move on to the next one. So, now in the last two problems that we talked about, we just considered that we have one input matrix, some n cross n, and we are doing some convolution with a filter of size f cross f, and we are getting some output matrix of size n dash cross n dash. But there we considered we had only one filter. But in case of convolutional neural network, we generally have more than one filters. Each filter captures different types of features from your input, let us say image. So, this problem will take that into consideration. So, here it is said that suppose you have 40 convolutional kernel, each of size 3 cross 3, and you are doing no padding and your stride is 1. This is the first layer of the convolutional neural network. Now, you pass an input of dimension 1024 cross 1024 cross 3. So, for example, you can think this is a color image. So, 3 channels are the RGB channels. So, each channel you have a 1024 cross 1024 matrix, and the 3 channels are RGB. So, this gives you the entire image matrix. Now, this is your input that you want to pass through the convolutional layer. What are the dimension of the data which the next layer will receive? So, basically what will be the output dimension after the convolution? So, initially you have 1024 cross 1024 cross 3 channels. Now, you are doing the convolution with size f cross f is here 3 cross 3. So, first we have to determine what will be the size of the matrix at the output of the convolution. So, for that, so here this 3 is just for the number of channels. Each channel you can consider as a separate 1024 matrix. So, each matrix will be convolved. So, each matrix will reduce in dimension based on the formula that we used. So, for each of these channels, the output matrix size will be 1024. We are not using any padding. So, minus only the f divided by stride, the floor of that plus 1. So, 1022. So, each of these channels will reduce to 1022 cross 1022. So, initially you had 3 channels, now you are using 40 convolutional kernels. So, each kernel will give rise to one channel. So, since you have 40 kernels, total you will have 40 channels at the output. So, this will be the output dimension. So, you will have to compute the first 2 dimension, which is the dimension of the each channel, from using that our n dash formula, using this and the filter size, and the third dimension, which is the number of channels, that is simply given by the number of kernels present in that layer.
Okay, so it won't affect that RGB3, right?
So, all those 3 will be combined in each of these channels. So, basically if you have these 3 as RGB, let us say these 3, and your kernel is, let us say, this much. So, this basically combines that stretch for all the 3 channels. So, this entire, all these values will be combined to give you the first value of the first channel of the output. So, just to give rise to one value. Now, you have 40 such type of kernels will be there. Each of those 40 will combine all these 3 RGB channels.
Okay, thanks.
Now, the next one. So, this is a multi-layer convolutional neural network. So, it is saying that let us consider a convolutional neural network having 3 different convolutional layers in its architecture. So, the filter size, number of filters, stride, padding, everything is specified for each of the 3 layers. Now, layer 3 of this network is followed by a fully connected layer. If we give a 3D image, or basically RGB image of input, RGB image input of dimension 39 cross 39 to the network, then what is the input dimension of the fully connected layer, that you have to determine. So, initially input matrix, the input matrix that you have, that is 39 cross 39 and it is 3D. So, 3 channels are there. First, this thing will go through the convolution in layer 1. So, can anyone compute what will be the output size for layer 1?
(37 into 37 into 10).
Yeah, correct. 37 into 37 into 10. Simply you make it go through the same formula. So, 39 minus the filter size 3, that gives 36, divided by stride is 1. So, 36 plus 1. So, 37. 37 cross 37 and you have 10 filters. So, 10 channels here, 37 cross 10. Now, similarly, what will be the output shape for layer 2?
(17 to 17 into 20).
Correct. And layer 3?
(7, 7, 40).
7, 7, 40. Right. So, this 7, 7, 40 matrix now has to be given as input to the fully connected layer. So, as I said last day, if you want to give such type of a matrix to a fully connected layer, all these elements of this matrix will be connected to each neurons of the layer. So, basically it is same as flattening this matrix and making it a 1D array and giving it to the fully connected layer. So, basically the dimension of that flattened array will simply be this 7 cross 7 cross 40, which is basically 1960. So, this will be the dimension of the input to the fully connected layer. So, that is it for this problem. Now, the next one, this is a simpler one. So, suppose your input is a 300 cross 300 RGB image and you are using a convolutional layer with 100 filters and each of them are 5 cross 5 filters. So, how many parameters does this convolutional layer or this hidden layer have without any considering any bias? So, can anyone tell me how many parameters does this layer have?
Two 96, right? 296 into 296 into 100.
That 296, I guess you are saying the output size, I guess. So, we here want to know how many parameters are there.
W. Okay.
Yeah.
So it's 100, right? 100.
Can you tell me how 100 filters are there? So, you are saying number of parameters is also 100?
Yeah, I'm thinking that will be set as a W weight because each movement, but each.
Okay, so basically what is happening in this convolution is, let's say if we draw this thing again. So, this is input, again a 3D matrix will be there because this is a RGB image. So, as I said, we'll place the kernel at different places and that kernel will combine all these elements from the three layers, all the 3 layers. So, this is basically it will do a weighted combination and the number of weights that it has, that's the number of parameters, because this same weight will be shared throughout. So, if this is a 5 cross 5 matrix, so you are here combining 5 cross 5, this is 5, this is 5. So, you will have to combine 25 elements, 5 cross 5, 25 elements. So, 25 weights will be there. Like that, you are combining 25 weights from each of the 3 channels. So, total number of weights will be 5 cross 5 cross 3. So, which is 75. That is for one filter. Now, like that, you now have 100 filters. This is for one filter. Similarly, you can have 100 different types of kernels. Each will have the same size because all same kernel size and all are there. So, total number will be 75 into 100. So, 7500 parameters will be there without bias. So, these are just the weights.
Okay.
Now, if we
so
want
the
to
5 into 5 into 3, that is the RGB channel, right?
3 is the because of the RGB channel. So, initially if the input matrix is, let us say, some 10 channel something, then you will have to be you will have to take 5 cross 5 cross 10, all those 10 has to combine. Now, if we want to consider the bias also on top of this, so each of these filter will have one bias term. So, we have 100 filters, we will just have 100 bias terms.
So this filter, I just have some small thing, like this filter is always kind of a 2D matrix, or it can be of any dimension.
It can be of any dimension depending on what is your input size. So, basically we do either 1D convolution, 2D convolution or 3D convolution.
Okay.
So, all these are possible.
Okay, thanks.
Let us move on now. So, now the next question is, what will be the range of output if we apply ReLU nonlinearity and then sigmoid nonlinearity subsequently after a convolution layer? So, I know that everyone knows the answer, still I will just do this. So, for ReLU we know that the output is basically max of 0 comma x, max of the 0 and the input independent variable, that is the output. So, if we just plot it, this side is x and this side is fx. ReLU is basically in the negative side of x, it remains in 0, in the positive side it is just a straight line with slope of 1 at a 45-degree angle, and sigmoid is basically fx equal to 1 by 1 plus e to the power minus x. So, if you plot that also, so that becomes like this, this is 1 and this crossover will be at half. So, here it is said that we first apply the ReLU nonlinearity, then we apply the sigmoid nonlinearity. So, once we apply the ReLU nonlinearity, we have everything as either positive values or 0, because this fx here in this case is only 0 or positive values. So, the input that is going to the sigmoid function, that is greater than equal to 0 always. So, if it is always greater than equal to 0, the input will always remain in this portion of the x axis. If that is the case, then the output can be anywhere in between this region. So, basically the range will be half to 1. Now, this is the last question for today's session. So, here we have the input image which has been converted into a matrix of size 224 cross 224 and convolved with a kernel of or filter of size f cross f with a stride of s and padding p to produce a feature map of dimension 222 cross 222. Now, you have to say what are the values of f, s and p. So, what kind of filter size and stride and padding you have to use, so that you get 222 from 224. So, if we just do it by looking at the options, these two options these have s equal to 0, that is stride equal to 0, which is kind of invalid thing. If you have stride equal to 0, your kernel is not at all moving through the input image. So, it is not making sense to do something with s equal to 0. So, these two are kind of impossible or like infeasible options. There are other two options are the only ones feasible. Now, here we can see that one has padding equal to 1, one has padding equal to 0. So, here your matrix size is reducing from 224 to 222. So it's most likely that no padding is being done, that's why it is reducing. So the most likely solution looks like this, but we should also check it. So if we check that, our formula wise, this was our formula. So we have 224 plus, let's say we take P0 minus F3 divided by 1 plus 1, 221, 222. So that's the valid option that matches, but anyway we can just arrive at the solution kind of by eliminating the others. So if you see the other remaining solution, which is this one, if you do this thing, it will basically not reduce the size.
224.
Yeah. So this will remain 224 itself. So that is not a valid option here. So this is the correct option for this particular problem. Okay, so these were the problems that I planned for today. So if you have any other doubts, we can discuss those. Otherwise, we'll close the session for today. Any doubts from anyone, we can discuss. Okay, in case there is no doubt from anyone, we can close this session for today. We'll meet again in the next week with the next set of problems. Mostly will be on some particular types of networks and some optimizers. Okay. Thank you guys for joining.
Thanks.